Good morning, everybody. Now we are talking about fire, so it will be hotter here. And first of all, I would like to give a floor to Tian Lee, our project leader, our fantastic project leader, kept all our friendly project partners together, and he will be online. So please, Tian.
Yes. So my name's Tian Li, research manager at ForestValue Research. So first, very sorry that I could not be on site.
Can we
Do you
also
hear
see
me?
the slides?
Yes, I can see the slide. So for the Firenwood, it's the background is I guess you're there, so you know wood is very important because the firewood is targeting the construction industry, which is one of the most resource intensive sector. And because wood is excellent construction materials, which is not only renewable but also sustainable, and with a very low carbon footprint. As you show, Alar showed the slides with those pictures, you probably already noticed some of the buildings. Those are the recently built buildings using wood. And the trend is like not only they're building more with wood buildings, timber constructions, but all those buildings are taller and bigger. So this means with this taller, higher, larger buildings, the fire risk associated with that need to be considered. That's why we have this project, Firewood, to address this issue. So as you can see, I also previously mentioned a little bit the aim of the project. So the aim of Firewood is basically to fill the knowledge gap related to particular the fire property or fire technical property of those engineered wood construction element. Because if it's in the case of fire, the temperature would be elevated. So that's the condition we're looking at. And in particular, the two objectives now is to provide a simple classification method for adhesive, and also to improve the design models for those construction elements like I-joints, like gluing rods, CLTs, and take the fire performance of the adhesive system into account. Because previously, a lot of people mainly focus on the wood part. We are now also focused on the adhesive part. So eventually, we hope to extend the application area and create a great market potential for engineered wood system. That's the overall kind of aim. So as you can see here, this is the kind of overall structure of our project. So we have a work package 1 on just to look at the strategy implementation obstacles, and we have work package 3 doing a lot of experiment, and the data goes into work package 2, and to help us to have the data to design a better models. And of course, in the whole process, want to disseminate, communicate, and also to create translational collaboration. And all this is managed in work package 5. So here is the last slides from my side. As you can see, it's a very diverse group. We have universities, we have research institute, and also companies. All of them are very well integrated in the project, involved in all the work packages, and very glad to work with all those partners. Thank you a lot. That's all my slides.
Thank you, Tian. You see, we are old-fashioned. We didn't pre-record any presentations. We are all alive here or online. So we do the presentations. So Tian mentioned a lot of testing, or we had the whole work package that was only consisting of testing. We did a lot of different tests, and the tests were, I will now give a floor to Robert Olofsson from Rise Fire Research Norway, also, who was responsible for all the testing. So he will explain to you what we did, or at least a big part of it.
Yes, thank you, Alar. Good morning. Yes, my name is Robert Olofsson, and I'm gonna do a presentation of at least the medium scale and the full scale testing that we have done. And I saw your presentations yesterday when you were shaking 18-story buildings. So I put the full scale in quotation marks because it's not really shaking buildings we're doing, but so first of all, I will just say about a little bit about the furnaces we used. For the medium scale, we have used a cubic furnace. It's 1.5 by 1.5 meters in the opening dimensions and horizontal plane. And for the full scale test, we have used two different furnaces, one vertical 3 by 3 and one horizontal 4 by 3 meters. All the furnace tests we have done, we have used the standard fire curve. You can see the diagram to the right. It's also called the cellulosic fire curve sometimes. And we also did a compartment test where we built a compartment inside a fire test hall. So for the first medium scale tests, we did loaded eye joists with the finger joints in the lower flange. And to the right, you can see that we are building the eye joist inside a box. And to the bottom right here, you can see a cross section of that with the gypsum board at the bottom. This was the exposed side. You can also see the position of the finger joints in the lower flange and the test setup. And how this worked, we had the loading system at the outer part, pressing upwards, and supports in these positions. I hope you can see my little red dot here. So the bending was going like a happy face here. And yeah, here you can see a speeded up video to the left. It's going right now. The test is running there. If you look closely, you will see how the eye joist is bending upwards, and it will soon break. As you're watching that, you can also see the box with the eye joist before the test to the right, and failure mode down to the right. We see the finger joints has ruptured or failed together with the wood. And also there's the diagram there just to show where we can measure the deflection to actually see when it's failure. For these tests, we measured temperature and deflection during the test, and after we measured also the failure mode and the residual cross-section. The video was looping. I hope you saw that. And we also did the test of CLT. Here to the left, we can see during the test, it's two elements on top of this smaller furnace. We ran these tests for 120 minutes and stopped. It's one-sided, also only from below. And for these tests, we measured the mass loss and also the shoring depth. To the right, you see, of course, after the test, and the element is standing on its side. I hope I'm holding the time. To the left here, we have glulam beams, two pieces loaded on top of the furnace. It's before we're putting the lid on. As you can see, what I'm talking with a lid, it's this part. Because we had three-sided exposure on these tests, sides and below, and they were run for 90 minutes. To the right, you see when we are lifting it off immediately after the test. And we also, for these tests, we measured the mass loss and residual cross-section. Moving on, we did also the full-scale tests, and these are very similar to how to test load-bearing constructions in fire resistance. And for this particular test, this was a CLT element. That's it's roughly 4.5 meters long here and 2 meters wide. And we have dead weights on top of it. It's loaded before the testing. And to the right and to the bottom, it's when we are lifting off after the test. The exposed side here to the left, you can see the underside of the CLT element. We ran this test until failure, meaning that they were breaking. And it was almost 2 hours test. Also did a similar test as the CLT, but with load-bearing floor with I-joists. Same setup. We have the dead weights to the left, and during liftoff, you can see the exposed side on fire. Also, for this test, we measure the temperature and deflection as you do in the test standard for testing these kind of constructions. And we ran the test for, I think it was 74, 75 minutes before we ended it. Similar, we did a load-bearing wall test. It's same measurements, temperature and deflection, but we're having the loading up here, pressing down with hydraulic. And to the left, you see the test after roughly 30 minutes, and to the right, it's after failure, of course. So for the last test with the full scale, we did a compartment test, and this was the room that we built inside a test hall. It was, I don't know if you can see it, like 5 meters, 4 by 5 meters to 2.8 meters high. And we measured the temperatures inside, and here's some graph example for that, but I will not go into detail on that. We had one opening in the room, you can see that also. The compartment during construction, to the left, erection of the walls and the floor, floors and the roofs. To the right, you have the inside view of the compartment before the tests, and the initial fire load was 16 Euro pallets stacked in 4 stacks. You can also see glulam beams standing here in the corners. This test, yes, you can see this was the beginning of the test. It's not the complete test there in 16 times the speed. But it's just to get a feeling on how it progressed in the start. The picture to the right, you can see the inside the room before extinguishing. You can see the glulam beam is on fire here. There's some cracks in the gypsum boards, and also some gypsum boards have fallen down. Yes, that was what I had.
Thanks.
Thank you very much.
Thank you very much, Robert. And I would also take this opportunity to thank you for all this, that you did all this testing during this Corona time, because many labs were just closed or limited possibilities to do something. But thanks to RISE Fire Research and Norway, then we could continue with at least some testing, at least with little delay, not so much delay in that part. So you did a great job. And you could imagine how many data we have now, and that's not all, so we have more. What we didn't tell you in the beginning is that we selected carefully timber. So the timber came from our two industry partners. It was certain parameters, certain density range, certain strength grade even. So we know almost the range of timber what we have, and then we had 11 different adhesive systems. We will never tell which products they were, which companies. We can say, but we don't say you which adhesive is what. But 11 very different from different adhesive families. Simon Eicher will explain it more a little bit later. So we compared the testing method actually, and we also, or one of our goals was also to try to find a simple small-scale test method to be able to predict the results in the full-scale fire testing. So I can now show you some test methods we tried in small scale with the same wood and the same adhesives, or let's say wood with the same parameters. And one of the methods was the so-called cone heater and shear test method. So we heated our specimens. The specimen is on your right. So we glued specimens 10 by 10 centimeter in plan, 20 or 40 millimeter lamella thickness. We glued them as parallelly, the grain direction or crosswise. We heated our specimens. We had thermocouples in the bond line. Here, these black dots you see are the thermocouples. So we measured the temperature. We heated until we get 290 degrees in the bond line. So almost the upper lamella was charred through. Something was left. And then we took the specimen beside and made a shear test. And we measured the shear capacity of the bond line or of the remaining char or wood. And we got different results with different adhesives. Here is one symbolic picture from our COVID times. This is the online investigations. So on the right side you have Trondheim, on the left side you have Stockholm. And what is going on is the investigation of the specimen after fire test, after small-scale cone test in Trondheim. And the lady you see here is Dr. Magdalena Sterli from RISE also, and she was one of our key partners. Fortunately, he could not be with us today. Just the simple reason she has holidays. But that's very important after such hard work. I would like to show you some results. We don't have time to show you all, and we have even not finalized all the test results. We have a lot of data, as you can imagine, but just one example here. So this is now a cone testing. Every dot means a different adhesive system. And you have now only the cone testing results. So the shear capacities in newtons. On the horizontal axis, you have the CLT or crosswise glued specimens, and on the vertical axis you have parallelly glued specimens, so parallel grain direction. And you see the difference here is about 1.5 times, roughly. So the parallelly glued specimens are 1.5, or the bond line is 1.5 times stronger. That's one finding, logical. This method has quite good repeatability also. Another method we tried is small-scale testing of finger joints, and we did statical tension loading when we heated the specimens under cone heater. You see the specimens at your left. It was one side exposure from fire from the cone heater. The lateral sides were protected with the stone wool. And then we had statical tension load. We tried 100 kilograms, 200 kilograms. There will not be a quiz afterwards, but just to get some kind of rough estimation. And then we measured the time to failure, and we observed the failure mode. Here you have some. That's fun for us always, to break something, to burn something. So this was now the time to failure moment. And then we followed or observed what was the failure mode, if it was the adhesive failure or the wood failure or mixed, and what was covering mode. That's also very important. Here we have all these 11 adhesives, the results from this small-scale finger joint testing under different loads, 100 kilos, 200 kilos. So every set is a different adhesive. You see it's a quite good repeatability within the group, but there is some difference between the groups. When we talk about wood failure or adhesive failure, so there are some examples. So this is a clear wood failure of this kind of finger jointed specimen. So you see the fingers are broken. It means that that was wood that broke in this test. And also the picture below, this is the cone heater testing I showed you before in the beginning, and that's a clear char failure here, it didn't fail in the glue line. But here you have clear adhesive failures. So the picture up there, the finger jointed specimen, so you see the clear fingers. So it means that adhesive was where it broke. So this is also very important when we apply this test method, so to observe the failure mode. When we compare these two cone heater test methods, then you see there is quite a good correlation between them. So we can run one or another to predict the results in full scale. And here are some charring depth results from the CLT furnace test what Robert showed you before. So 2-hour test, CLT slabs, one side via exposure, and the charring depths on the vertical axis in millimeters. And every number here shows the different adhesive. So you see that there is difference in charring depths. On the right side, you have more charring depths. It means that wood is always the same, so it means there is some difference in the behavior of bond line when the charring goes through the bond line. If you take the known charring rates that the engineers always know, so 0.7 millimeters per minute, then we could get this charring depth at the end. So the red line shows you 0.7 millimeters per minute, so some of them, the adhesives are over. And what we are trying to do is to predict this behavior in the furnaces by our small-scale methods. And here you have some examples where we compare the cone heater shear test method on your left, or cone heater finger joint method on your right, and the vertical axis shows the charring depths of CLT we get from the furnace. So there is a correlation. And the letters, the C or A, it means the failure mode from char or from adhesive, or W means the failure mode of wood failure or adhesive failure. So based on these investigations in small scale, so we would like to propose, or we propose a small scale method for testing adhesives, for developing adhesive systems, for structural purposes. So this finger jointed tension static loaded method could be a good method to predict the adhesive behavior in fire, and we are able to predict the behavior in the furnaces. So this method is at the moment also proposed for the Eurocode 5 Part 1.2 as one possible method for assessment of the bond line integrity. By that, I would like to give a word to Dr. Simon Eicher from Stuttgart, and he will explain you also more about adhesive we used. And please, the floor is yours.
Thank you. A very good morning to everyone. I'm happy to talk to you on tiny specimens now. You have heard something about large specimens, so-called small specimens, and now you will see some results on tiny specimens. As you may know, adhesive testing today for all structural products is done with small specimens, and the maximum temperature we address today in structural adhesives in Europe is 90 degrees, and for most adhesives only a temperature of 70 degrees is verified, irrespective of what generic adhesive family we have. Our basic idea was to incorporate elevated temperature tests in the range of present tests we do to avoid large-scale experiments and to make the tests repeatable with lowest possible bias, and then to serve as an input for Eurocode 5 Part 1.2. Maybe for the following, you have to bear in mind that the maximum test temperatures for adhesives in North America are 220 and 232 degrees Celsius, just for a reminder. Sorry. These are the number of adhesives we tested. We have at the moment 3 major generic types of adhesives: the polycondensation adhesives, which is phenolic resorcinol, melamine urea, and pure melamines. And then we have the polyaddition and polymerization adhesives, which are one-component polyurethanes and EPIs. And then we also have 2 components. I'm not talking about this now. So in total, we have 13 adhesives which we tested. Now here you see the tiny specimens we looked at. So we had compression shear tests, scarf joints, finger joints, and lap shear tests. And in total, just to give you an idea, we had with this number of adhesives, we had more than 2,000 small-scale tests. Now, the first one is a simple block shear test, which follows the provisions given in EN 17224, which is, say, a copy of the American standard 7247. These tests provide a test principle, but they do not specify target temperatures, and they specify an evaluation procedure, which, however, is not addressed to any classification of the adhesive. So we tested in different series these block shear specimens up to temperatures of 270 degrees. The specimens are heated, unloaded at up to 15 minutes, or at 15 minutes at the target temperatures, and the time to reach this temperature is slightly different varies with the applied temperature, is in the range of 25 to 45 minutes. What is important to say that the specimens are pre-tempered for 48 hours at 60 degrees and have, when the test starts, whether it is at 20 degrees or 270, they have a starting moisture content of 1.5%. Here you see now some change of the specimen color, and bear in mind that the upper row at each temperature is a so-called polyaddition adhesive, and the lower one is an adhesive which has a polycondensation curing behavior, so a PRF or a MOF. So what you see is that, of course, that the color changes drastically, and there's also the failure plane and the bond line is significantly different. For instance, when you look at the 270 degrees, where in the case of the polyaddition adhesive, you see a kind of melting of the adhesive, whereas the lower one, which is an MOF, still a lot of fiber breakage can be seen. Now, this is the reference behavior of solid wood specimens, which are completely matched to the wood which was tested with the bonded block shear specimens. And you see a quasi-linear behavior of the wood down to 270 degrees. And the bilinearity you see here comes from the tempering. If the wood wouldn't be tempered, the line would go straight up to a strength at 20 degrees, we all know, which is in the range about 9 to about 12 newtons per square millimeter for clear solid wood. These curves for solid wood serve as a reference for the following tests. So these are the bonded specimens, and here you see not insignificant differentiation of the individual adhesives, especially beyond 200 degrees. And this is the references for the solid wood, and we see that there is a not insignificant difference for many adhesives. If we here it's a different evaluation representation, and what you see especially at 270 degrees, you see that from the relevant 12 adhesives, 6 still have not insignificant residual strength of about 30%, whereas 6 other ones have almost no residual strengths. It should be said that the 6 who have considerable strengths are polycondensation adhesives. Now, a completely different test was the test with scarf joints, where we tried to idealize the behavior of a finger joint in small scale, which can be produced in a laboratory before going to a company. And this geometry was aligned to the, bread and butter test specimen of today's adhesive testing, according to EN 302 part 1, a simple lab shear specimen. And we tailored a scarf joint specimen out of that. And it looks simple, this specimen, but it was quite a way to come to that shape. And what is most important also in this test, we didn't load the specimen after they were heated, unloaded. We loaded the specimen within the heating, within the hot temperature regime, as you can see here. So we have a target temperature, which is maybe in this graph 200 degrees, and then the specimen is brought into that chamber, is loaded, and it takes about maximum 10 minutes that the specimen reaches the target temperature. Then the load is sustained for 45 minutes, and unless it's broken, the specimen is then ramp loaded to residual strengths. I should say that the load level applied is 30% of the mean ramp load strength. So these tests were performed with the temperatures you see here, so up to maximum of 250 degrees. Just for manufacture, that you see how such a specimen is made, you scarf joint a larger block, and then you slice out the smaller specimens from that larger block. This is some views of the test, and here now some results. Here you see that the maximum temperature, apart from number 3, which has to be investigated a little bit more thorough, and it was due to mostly due to the wood, that all scarf joints lost complete capacity up to at 250 degrees, whereas other adhesives lost the capacity much earlier at 200. And please bear in mind the sequence of failure was very close to the sequence of the failure I showed you in the block shear specimens, and it's just the temperature magnitude is shifted somewhat to lower temperatures due to the superimposed loading. This is another representation of the results you have just seen. So almost no residual strength at 250, and the specimens remaining intact at 232, where a residual strength could be tested, were exclusively polycondensation adhesives. Now, instead of doing scarf joints, we can also do finger joint tests. Of course, these finger joint tests have to be scaled down to be done in a test chamber where you have a surrounding heating chamber, and this was done by slicing small slabs from industrially manufactured finger joints, which were produced with all the adhesives at Mulven, at Monzonite beams, under industrial conditions, which was a really perfect situation, because, as you know, it's not very easy to change adhesive in an industry company. And these are the test results. Now showing you that at 232 degrees, no specimen remained intact. The loading scheme was the same as for the scarf joints. The temperature stability of the adhesives reduced even further. Again, the adhesives which showed a decent capacity at 200 degrees were throughout of one already named generic adhesive family. That is the results of the finger joints, which complies quite good with the results of the scarf joints. Finally, we had the idea to do the most simple test. And some of you might ask, why didn't we do these tests at the beginning? Now, you don't get a test from a European funding agency when you say you perform a well-established test and you just change the temperature, then you would get no penny from them. Finally, we had this in mind, but we had to do this at the very end, just to see what happens if we extend the present temperature range of established tests to presently not investigated temperatures. And it is two sequences of tests. The one in one sequence or in one sub-test series, the specimens are heated and then loaded, and in the other, indicated by the green block here, first the specimens are heated up under loading. This green block hasn't been done so far. Again, we ran out of specimens. As I said, 2,000 specimens was quite a number, and it was, of course, intended to have a very clear matching of the bonded specimens with the solid wood. So we could do these specimens only with 6 specimens, and it is noteworthy to say that it is 3 polycondensation adhesives and 3 polyaddition adhesives, which where you can guess what the polyaddition adhesives are in this graph. Not to highlight it too much, but there is also one polyaddition adhesive which is behaving quite good, and for an insider, it's also quite obvious why this adhesive is better than the other polyaddition adhesives. So this is the result of the lab shear tests, and we are quite sure that we can come up to a reproducible, bias-free testing and classification of adhesives, either based on the tests according to 17224 or with these simple lab shear tests, as serving for a classification of adhesives. And here I show you a tentative table for a future classification of adhesives. This is based on the block shear specimens according to 17224, and where the residual strength of the bond line is related to the residual strength of the solid wood, which shows a very small, fairly small scatter. And at the moment, I wouldn't like to go in depth to this, because of course there is consequences for industry and also for Eurocode. So finally, I would say we are in a project in a stage where we have these large-scale specimens, we have the medium, and we have the small, and now it's up to us to wrap up everything and to come up with a solution where we can show that most of the results are compliant. So thank you very much.
Thank you, Simon. So as you see, we have now a lot of results. We are in a unique situation that we have done a lot of different tests in different scales with exactly the same adhesive systems and exactly the same wood, or more or less exactly the same wood. That was not done before. Our project is not finished, and we cannot show the final results, but what you show or saw now, it's very promising and very interesting results we have. There is a whole summer with the analysis in front of us. Another part of our Firenwood project was the bonded in rods, bonded in steel rods. So we did a different or separate part of this project in Munich, and Patrick Dumlers will be online now, I hope, and will present this part of the project. So hello, Patrick, and please, the floor is yours.
Hello. Thank you for your introduction. I hope you can see my screen. As Allah said, we investigated the fire behavior of Luden rods. And there's a specific type of connection because 3 materials are in interaction: the timber, the adhesive, and the steel rod. And this type of connection has different advantages, like a high stiffness and strength. but also optical, because you can see the connection because it's lying inside the timber. And another advantage is that it's protected from environmental inputs and fire. And there are many design models for standard conditions existing, which consider different parameters like density or borehole diameter or stiffness of the adhesive and so on. But there are no design models for the case of fire yet. And therefore, we concluded a test campaign consisting of 4 different tests, which were small-scale tests in tension and creep under temperature loads, fire tests with different design of the specimens and without mechanical loading under standard fire curve. The third one were creep tests with specimens with glued-in rods, but with temperature load. And the fourth test series is the same like test series 3, but under standard fire curve. And for test series 1, there were 2 different setups, like what they did in Stuttgart. First of all, the tension test under elevated temperatures. There you had the specimens heated on different temperature levels, in our cases from 20 to 110 degrees, and afterwards tested with a mechanical tension load until failure. And for the creep tests, this was different. There the specimens were loaded mechanically at first at a constant load, and afterwards a heat was applied of 110 degrees. We had 2 different adhesive types and 3 different glue line thicknesses of 0.1, 1.0, and 3.0 millimeters. And per test series, there were always 10 specimens. But the results showed also that we had a post-hardening effect due to the heating duration at the tension test under elevated temperatures. So we concluded 4 additional tests to investigate tempering. Here you can see some of the results. These are specific for the glue line thickness of 1 millimeter. On top is adhesive 1, and at the bottom diagram you can see adhesive 2. And the test showed that you have already at 60 degree strength reduction of the adhesive. But it also showed that the strength and the stiffness behavior is dependent on the adhesive type, because, for example, for 70 degree, you can see that adhesive 1 already lost about 60% of its residual strength. Therefore, adhesive 2 has almost 80% left. And in the red circles, these are the test series for the post-hardening effect, which were 3 at temperature of 70 degrees. There, the specimens were heated to 70 degrees and then left in the oven for a specific amount of time. And for the series with 90 degrees, the heating phase or the heating time was longer. It took about 1 hour, and for the fast test at 90 degrees, it was only about 10 minutes. But can also be said that the post-hardening effect is not relevant for the case of fire, because we don't have the slow heating of the specimen there, but it can be suitable as an additional treatment to raise the temperature limit of the different adhesives. Here you can see some results for the creep tests. These are the failure temperatures of the different specimens. The blue ones are for adhesive 1 and the green ones for adhesive 2. And there you can also see that adhesive 1 has a slightly lower failure temperature. And the test also showed that the failure temperature is lower than for the tension test with elevated temperatures. So the testing setup has also influence on the results. For test series 2, we had different fire tests with glued-in rods. They were either one-sided, exposed to the fire, or four-sided in the case of C. And these tests should show the temperature development inside the glue line for different variations of the connection. We differed between the diameter of the rod and glue line thickness, and especially for the series B, we had different coverages of the rods, so they aren't exposed to the fire directly, like with gypsum plasterboards or different wooden plug thicknesses. And then there were thermocouples inside to measure the heat. And the test results were used to adapt the material parameters in the numerical simulations. So we could simulate the heat development inside different type of connections. Here you can see the specimen. It was a sealing test where all specimens were connected together. On top, on the left side, you can see the thermocouples on top of the specimen. And on the right side, the specimen after the fire test with charcoal layer and after it was cleaned. Afterwards, there was test 03 with glued-in rods in creep test conditions. We had 34 specimens. Some of them were tested under standard conditions at room temperature. So we had an amount of load level to apply during the creep tests. There were also 2 adhesives and 2 different glue line thicknesses as usual. And we differed between 2 different cross sections dependent on the rod diameters between 12 and 20 millimeters. The load levels were 40% and 60% of the mean value of the residual tests. And the residual test showed that a thicker glue line results in higher shear strength, but only for the cross section in the case of 100 millimeter. Was about 15% higher than the test with a 1 millimeter glue line thickness. And it is assumed that normally this should be the same case for the smaller cross section also, but there the failure occurred always in the timber with cracks. So normally the cross section there should be increased to see if then the thicker glue line results in higher shear strength also. And the test also showed that adhesive 2 has a slightly lower strength than adhesive 1. Here you can see the failure modes on the left side for the tests at room temperature and on the right side for the creep tests. The orange color is for wood failure as a main source of failure mode, and on the right side the blue color is for adhesive. And it's obvious that adhesive is decisive for the failure of the connection when temperature is applied. And based on these results, limit temperature was derived to, it can be said that this limit temperature shouldn't be reached by the glue line, so the connection won't fail under temperature load. And the idea for the design model was to have a minimum side cover, so this temperature limit wouldn't be exceeded in the case of fire. Based on the parameters deduced from the test series before, we made different numerical simulations to see how much side cover is needed for different rod diameters and glue line thicknesses, and also for different fire load times for 30, 60, and 90 minutes. And based on these results, the test series 4 was planned with the minimum side cover for these glue lines. But as Ala said, the testing facilities during COVID were locked down or didn't have enough capacities. So these tests are delayed and still in progress. So the validation of them is still needed, but yes. And with this, I want to thank you for your attention, and I think I can pass on to Katrin.
Thank you, Patrick. I hope you heard also the applause you got. And thank you for your work in the project. So you really see we burned a lot of ForestValue money in our testing labs, different labs. But another topic we did and we looked at was the design models, to improve the design models for the engineered wood. And one good example is from the engineered wood is the highly optimized eye joists, where you really use every square millimeter of the wood. And our PhD student and researcher from Tallinn University of Technology, Katrin Nele-Mäger, will explain you now a little bit what we did with the design models. So please, Katrin, the floor is yours.
Thank you. So, hello everyone. I have to say this is my first time speaking in a theater, so you are quite invisible to me. Very, very low pressure today. So finally, I will talk about the design models that we have developed within this project. What is the topic of my PhD thesis is the development of a fire design model for light timber frame assemblies with eye joists. Here you can see an overview of what the model means. So we usually use eye joists in assemblies with, is this the laser? Yeah, with thermal insulation and some protection on the fire side, so either a gypsum board or any other combustible or non-combustible material. And then depending on that, we will have different phases in the charring. So this graph represents the different phases of the development of the char depth on different sides of the eye joist. And then finally, since the actual shape of the charred flange of an eye joist is round, we will transfer it to a more comfortable rectangular cross-section, so for the ease of calculation. As I mentioned, charring can have different phases. So here we're looking at charring from the fire side. So depending on the properties of protection materials, as I mentioned, for example, gypsum plasterboards, also depending on the size of the flange, they can be really small, starting from, let's say, 40 millimeters by 40 millimeters up to 100 times 50. That's roughly the range of sizes commonly used with eye joists for the flange. Then depending on the size of the flange and the protection, we will have different charring rates from the fire side of the eye joist and also from the lateral side. So that's mostly affected by the properties of thermal insulation. So the more fire safe or the less combustible a thermal insulation is, the more it's able to continue to protect the sides of the eye joist even after the fall off of any protection materials or any boards. And that can also happen in different phases depending on the combination of materials used. And within this project and within actually my PhD, which is unfinished yet for anyone interested, I have worked a lot on developing these expressions for each of these parameters that you have seen so far. Also, what we need to stop from happening is the occurrence of the charring of the web, because the webs are quite thin. They are ranging from, let's say, 8 to 12 millimeters in thickness. So once the fire reaches the web, it's quite soon that we will also have load-bearing failure of the whole assembly, of the whole load-bearing capacity of the I-joist. Speaking about load-bearing capacity, we also have to consider, in addition to the charring, we also have to consider that timber will reduce in strength and stiffness as the temperatures increase. That also happens before charring, as you can see on the top right-hand side. These are from the Eurocode 5 part 1.2, the reduction factors for strength and stiffness properties, depending on temperature. So the reduction of strength, as a simplification here, is considered in the design model by a zero strength layer, which is a kind of a fictive additional char depth, and the depth of the zero strength layer depends on the load case. So if it's a bending member or a compression member, and depends on the type of insulation used, for example. So that's how much kind of heat is stored, or heat is coming into the flange, which decreases the strength. And also, the biggest topic of this project is that the strength of the zero strength layer depends on, the depth of the zero strength layer depends also on the adhesive performance. So for example, as you saw from Robert, these tests with the I-joists in bending where the finger joint was in tension, then the adhesive performance plays a large role in the total capacity. So we have developed 3 finger joint classes, and there's a paper also at the WCT 2020 or 2021. It was postponed again due to Corona. Never getting over the COVID excuse. I mean, that still carries us. So yeah, the finger joint classes depend on the performance of the adhesive. In wall joists, we have also made some further development because especially if the first board falls off, then there is no lateral stability provided by any bracing on the fire side. So then we will have something like a torsional buckling kind of behavior. And we're investigating that further also with simulations. But going into more general, what are the design model, or what are the results of our project that affect different design models? So as it has been kind of hinted at, we have different performance of adhesives. So I will give you now some terms, some definitions that are kind of like the hints for the new Eurocode 5 part 1.2, which is the fire design standard for timber structures in Europe. So there's 2 types of classifications for face bonding. First is that the bond line integrity is maintained. In that case, we consider that the adhesive does not soften faster than the char, and that means that we can calculate the char depth as a constant rate. The second is where the bond line integrity is not maintained, so that means that the protective char layer will crumble off, and then we have to consider in our calculation of char depth something called the step model. And this is also similar for I-joists. So if we have not maintained, then we have to increase the zero strength layer depth. And that means that we will have a shorter fire resistance time, short or less resistance in less load-bearing resistance in fire. One new result that we have had is the proposal for glue laminated timber. Up until now, we have not considered the bond line behaviors or the effect of bond line integrity for glue lam, because we have never seen that explicitly in tests that can be a problem. However, with our test series, we had observed also some adhesive systems, some bonding systems which do exhibit the fall off of charred layer also for glue laminated timber. I know that will be a unpopular result. However, I think we all agree that we want to have safe design methods. And we don't know what will happen in the future. Maybe in 7, 10, 15 years, we will have even less resistant adhesives, which may have better performance in many other fields. But this suggestion to be able to use also this, to consider the fall off of charred layer also for glue lam, it's not a negative thing as a whole. It's just that we need to have the capacity to consider these effects in all different cases. So the difference is the use of different charring rates. I will probably not go into too much detail because I think we would like to have some time for discussions as well. But also on the sides of the glue lam members, then we will still consider, we propose that we should still consider a one-dimensional charring rate, so a constant speed. So finally, I will show some comparisons with the step model and with the constant char rate. So we have 30 millimeter lamellas, and the green line shows an example with an adhesive which does not maintain bond line integrity in fire. So here at the 30 millimeter thickness, we have fall off, and we will consider a faster charring rate. So this is kind of the step model. If we are able to develop a 25 millimeter thick char layer, then we consider that the charring will kind of slow down until the basic charring rate. So these two lines are parallel. And with thicker lamellas, so the blue line has 45 millimeter thick lamellas, there you will see that the difference is less. However, I would like to point out here that for 30 and 60 minute fire resistance times, the differences are not so large between the bond line integrity maintained and not maintained adhesives. So these differences will be more relevant for longer fires. Yep. The similar graphs, more analytical with charring coefficients depending on the charring phases. And what we are now discussing is the post-protection coefficient, which is called K3. So we're considering if it has to be 2, as it is right now, or if it can be a different, less than 2. Because here, if we look at the test results, you can see that we are more or less between the bond line integrity maintained and not maintained in the calculation. So maybe this, maybe the slope of these parts of the charring graph are maybe a little bit too steep. So we can maybe bring them down a little bit as well. But that's ongoing. The end of the project, I think, is somewhere in the autumn, so stay tuned for that. And as a conclusion, I would say that we have developed simple classification methods for the adhesives. We have proposed them, and also fire design methods for I-joists, for CLT, for glue lam, and glued-in rods, considering the fire performance of adhesives have been improved. And to mirror what Tian said, I hope that we have extended application areas for engineered wood systems. And thank you very much. I think we have some discussions.
Thank you very much, Katrin. I would now like to ask all our partners to sit on the scene, and we are ready for your questions. And we try to give some answers. Before starting with questions, I would also like to very much acknowledge and very big thanks for our adhesive companies who helped us with their adhesives. Without them, we couldn't test anything. So Akzo Nobel, Dunea, Gielte, BASF, and Henkel were the adhesive companies who helped us, but we will never tell about the products we tested, because we have to keep the trust, and that's why we keep it confidential. So what we do in this project, we compare the test methods, not the adhesives. But now we are ready for your questions.
Thank you very much for a very interesting project. I was just wondering, so there's a lot of Scandinavian expertise in that and German expertise in the project. So the species, the wood species that you tested, I only spotted on one slide that there was hardwoods in there. So was it a mix or was it mainly concerned with softwood?
Mainly softwood.
It was mainly softwood. We had the project leader from Norway, so it was a Norway spruce. Yes, question there.
Yeah, Robert Jokwa from Chalmers University in Gothenburg. Maybe a follow-up to that, because adhesive tests at normal room temperature, they are partly done on beach specimens. And I could imagine that, of course, at elevated temperatures, these different wood species behave different, and maybe also the adhesion to the different wood species behaves different. I mean, is there maybe also a need to adjust some of the specimens, or I mean, to combine the actual wood species in use later with the wood species that is used in the test, in the fire tests?
Simon, I guess you can mention that. Oh, can't hear. I'm still online. I think you have also been through that at least in your test.
Maybe a short answer to this. We showed you the small scale lab shear tests with according to Ian, 02 part 1, with the beach specimens, which were highly consistent with the compression shear tests which were performed with spruce at the beginning. So I'm convinced that the results in general can be transposed to a certain class of hardwoods, but those who are fairly easy to bond, but not to all hardwoods, definitely not.
Yes, thank you.
Yeah, thank you very much for this interesting project and the findings. I'm Udo Sotter, and coming from the resource side, located, or I'm working at the FVA in Freiburg. And Simon expressed somehow that there will be reactions on your findings in terms of adhesives, which will be rated on a top level possibly, and some will fail for the future. Is that a right interpretation of your presentation?
Yeah, one could come to that conclusion, yeah.
Yeah, we have to define what is fail, because you saw also that we are proposing different design models according to adhesive behavior. So you just have to choose the right model. So no adhesive is failed or is not rejected for the market. No. Just you have to show, or have to choose the right design model.
But to add, if we accept that we have a temperature close to the bond line in the range of 250 to 300, and if the adhesives behave significantly different, and the ones lead to, say, a similar behavior as solid wood, and the others lead to a premature fall off, then of course there is a full justification for a step model and for a kind of differentiation. And this differentiation so far is done in North America quite rigorously. We in Europe had a different approach to this situation, which of course will change, and we try of course to minimize the impact on existing industry, but I think with the increased importance of timber structures, I think this is a very relevant issue. For instance, this morning when I didn't have got up too late, so I didn't have time for real exercise, but I ran down the fire stair. I was from 18th floor down, and it was it's a completely open timber in the fire staircase, and I would like that the screws and everything and the planks are still intact when I should have the necessity once to run down. If I wouldn't like to, but yeah.
But these walls, staircase room, these has fire treatment.
One? It has a fire treatment, yeah, but this...
there will not be a fast fire spread.
Nevertheless, I would like to... The fire, that's another issue. The fire treatment normally has to be tested for compatibility with the adhesive.
Okay, thank you very much. Do we have more questions from the audience? Seems not. It has been a quite intensive 1 hour and 20 minutes. A lot of information. So thank you from our side. Thank you all the partners, and Tian and Patrick also. So.
Yep. Thank you, Tian, also there behind the screen, and thank you, Alar, for following the timetable exactly, and thank you for the whole team for your presentation.